3 questions for homework over the weekend here, 12, 13, and 14 on page 268. We want to go over question number 14. The question says 2 pulleys are connected together by a belt as shown in the diagram below. The pulley connected to the motor spins at 200 RPM. What's the frequency of the larger pulley? And they give you a hint here. Okay. I'm not sure that they should have given us that hint. We maybe should have figured that out ourselves, but in the end, they give us the hint, so we'll go with it. It says both pulleys have the same velocity at their outer edge. That's actually not quite right. Okay. That's not quite right. Okay. Their intent for the statement they just made is correct, but they made an error in a word that they used there. Both pulleys have the same velocity at their outer edge. What's the error in that? What's the error in that, Alan? Yeah, it should be speed, because the direction isn't the same, right? At any given point necessarily. So we're going to say that both pulleys have the same speed at their outer edge. Where are we going to go with this? Where are we going to go with this question? We know that as an object is going around in a circle, in uniform circular motion, it's going at a constant speed, it experiences a centripetal acceleration, in other words, an acceleration toward the center of the circle. It experiences a centripetal force, a force toward the center of the circle, and we can describe both of those acceleration and those force by an equation that we learned last week. But it's not good enough just to say, well, look, F is equal to mv squared over r or something like that. There's something else that we got to catch here. What is it? Like, what do you want? Where do you want to start with this? There's always somewhere to start for every single one of us. We know that there's a centripetal acceleration. We know that there's a centripetal force. We're talking about frequency and speed. We know that speed is 2 pi r over t. Let's try something that's valid. And let's try the 2 pi r over t thing. I got a gut feeling on that one. V is equal to 2 pi r over t. First of all, because they talk about the speed being the same at the outer edge. Second of all, because they talk about frequency, and although frequency is not period, it's close. So I got a gut feeling on this one. In fact, I'm just thinking about this now, I have a gut feeling on something else as well. It says both pulleys have the same speed at the outer edge. Let's say this is the speed of pulley 1. Let's say this is the speed of pulley 2. And therefore, let's say V1 equals V2, since they have the same speed on the outer edge, right? We can do this. Everybody can start with this. Everybody can. And if you're thinking a little bit more, then you can probably set V1 equal to V2, considering they tell me they have the same velocity or the same speed. So let's do this. Let's say 2 pi R1 over T1 equals 2 pi R2 over T2. I'm actually going to cancel a couple things. I don't have to, but you see anything here that I can cancel out? Remember, to cancel something out, it has to appear in every term. Yeah? Yeah, I can cancel it to 2 pi because it appears in every term on both sides, right? So it becomes R1 over T1 equals R2 over T2. Now, honestly, not everybody's going to get to this point, right? And not once have I said that everybody should be able to solve every problem. But I've said everybody should be able to start every problem, right? Everybody can recognize V is equal to 2 pi r over t and at least get a start on this, at least get a point for showing a little bit of work on that. All right, we don't know what T1 is, but you know what, we can find it. Let's say T1 is equal to 1 over F1. So 1 over the first frequency, which is going to be 1 over 200 revolutions per minute. We got to convert that to revolutions per second. What's that equal in hertz? 200 divided by 60 is 3.333. All right, so let's say 1 over 3.333 gives me a period of, what is that, 1 over 3.3333? That works out to be 0.30 seconds for the period. All right, so let's sub that in. R1 is 0.10 meters divided by 0.30 seconds. R2 is 25 centimeters, or 0.25 meters divided by T2. Now, we're not actually looking for T2, we're looking for F2, but we know that once we get T2, the period of the second the second pulley, then we can find F2 pretty easily from that. So let's calculate T2 now. It's cross multiplying, really, right? T2 goes up by multiplying, the 0.1 goes down by dividing. Right? Taking that up, taking this down, and this goes up by multiplying. So T2 becomes 0.25 times 0.3 divided by 0.10. This is 0.75 seconds. And now once we've got T2, we can find F2. If T is 1 over F, then F is 1 over T. So we're going to say F2 is 1 over 0.75 seconds. And that gives me 1.3, two significant figures because of this, right? 1.3 hertz. The first one was moving at 3.3 hertz. The second one is moving at 1.3 hertz. We should have made a prediction before we did this, actually, as to whether it was going to be a higher frequency or a lower frequency. Clearly, it's a lower frequency. Can anybody tell me why it's a lower frequency, or if we had have made that prediction like we should have before we started the question? Anybody tell me why you would have predicted a lower frequency? Yep. Good. That's a great answer. It has a larger radius, so bigger circumference, which means if it's moving at the same speed, it takes more time to make one rotation, right? If it was moving faster, then all bets are off, right? But if it's moving at the same speed, it takes more time, therefore bigger time means lower frequency. How many people actually got the answer to that question? 1.3 hertz. Anybody? A few people did. Good. Did you guys do it more or less like I did it? Completely different? You guys did do it the same way, more or less? How'd you do it? You multiplied the 200 RPM by what? Yeah. Okay, that works. That works if it's a linear relationship between R and V. Okay. Yes, that's exactly it. Now, if you're thinking about all that as you're doing that, then that's fine. I'll caution you on that method because sometimes that method can lead you astray if there's a squared relationship in there or something like that. But if you recognize that it's a linear relationship and you're consciously thinking, oh, it's linear, therefore, then absolutely. I'm not going to try to explain that to everybody else here because although I know exactly what you did and it's a good method, it's almost more of it's as much a math method as it is a physics method. And I think I want these guys to see the physics part there. But that's good. If you can think about that, then that's fine to do something like that way. Good? All right, we're going to move forward a little bit here. Last week we talked about uniform circular motion, solve problems involving centripetal acceleration and centripetal force. Today we're going to do the same thing, but we're going to talk about that in the context of what we call vertical circular motion. We're talking about May 31st, sorry, Tuesday, May 31st, we go to our amusement park physics field trip. We're going to do a lot of problems involving vertical loops on roller coasters. We're talking about objects going in circles, but upside down circles as opposed to horizontal circles. Remember last week I kept swinging the keys around my head? Okay, that was the circle that I used. Okay, that's a horizontal circle. If I start swinging the keys around like this, that's a vertical circle. Okay, and the analysis changes a little bit. Okay, the equations that we learned last week still apply, but we have to do a little bit more with them. We're going to analyze objects going around these vertical circles in two places. The reality is an object has an infinite number of places that it can be as it goes around the circle. It can be here, it can be here, it can be here, and so on. It has an infinite number of places that it can be, but we're going to pick two places to analyze. The top of the circle and the bottom of the circle. Now you can see that I've got these drawn as little cars on a track, but it doesn't have to be cars on a track, right? It could be anything going around a vertical circle. The keys on the end of my string, like this. Anything going in a circle that goes upside down. Now, the reason that I'm going to analyze these two parts and not every other infinite part or spot where this object can be as it goes around a vertical circle is because these are the two extremes. The top and the bottom are the extremes. We could analyze anywhere else along the path using a little bit of vector analysis, but we don't need to because the values that we calculate fall in between the extremes. So let's just go with the extremes, the top and the bottom. Now, let's analyze the top first here. This object at the top of the circle, whether it's my keys on the end of the string, the lanyard, or whether it's a car on a roller coaster, this object at the top of the circle experiences multiple forces. The first force that it experiences is what? The most obvious one. Gravity. Gravity. And gravity acts down. Let's label that force of gravity downwards. In fact, while we're at it, we might as well label gravity on this one as well because it's acting down in both cases. Gravity always acts down. Remember, even when we had the inclined plane where the car was at an angle, gravity still acted straight down. What other force might I have acting here, though, at the top of the circle or at the bottom of the circle for that matter? What other force might I have acting? Any ideas there? Nick, can you think of another force that I might have acting here? Good. The normal force, the force of the track. Okay, if it was a roller coaster car on a track, it would be the track that provided the normal force. If it's the keys going around in a circle like this as I swing them around, it would be the string that provides the normal force. But there's a normal force. Good. Excellent. Natalie, which way would the normal force be acting when this car or keys or whatever is at the top of the circle? No, not acting up. Okay, you're going along this track like this. Okay, the track is above you. Which way is the track pushing you? It's pushing downwards, right? It has to push you downwards, right? If it pushes you up, then it's going to have to be down here pushing you upwards, right? And it's not. So it's got to be pushing you downwards. Now, how big is it compared to the force of gravity? We don't know. Depends upon how fast the object is moving. We'll just draw it at whatever length we want, really. Which direction would the normal force be acting, though, when you're at the bottom of the circle? Julia, which direction would it be acting down here? Up, yeah, because the track has to push you from at 90 degrees from where it is, right? So that's downwards when you're at the top of the circle, upwards when you're at the bottom. I'm going to draw the normal force here, bigger than the force of gravity. At the top, we don't know how they compare in value. At the bottom, the normal force must be bigger. If the force toward the center is smaller than the force that's taking you away from the center, then it isn't going to go in a circle. So as long as it's going in a circle, the net force has to be toward the center of the circle. All right. What do you think you do? What do you think you do next for either of these situations here? What comes next? And I'll give you a hint. We've done it a million times, even though we haven't done it in this context before. Good, excellent. F net is equal to the sum of the forces. We've got a free body diagram drawn in both cases where we have multiple forces. Let's say F net is equal to the sum of the forces. Fg plus Fn. So the bottom is going to look exactly the same, right? F net is equal to Fg plus Fn. Now we got a difference in direction between the top and the bottom. That's okay. We'll deal with that later on when we go to sub numbers in. Some of them become positive, some of them become negative. But the basic equation is the same. What's the next step? What's the next step in solving one of these problems? Okay, if it's in the context of vertical circular motion or in the context of an inclined plane or a pulley or whatever, what's the next step in solving one of these problems? Ben, what's next? F net is also equal to what? F net, Cameron, is also equal to what? Force. Mass times acceleration. Good. Mass time. Hold on before you write this down, though, guys. It's equal to mass times acceleration, right? Fn plus Fg. All right. The acceleration here we're talking about specifically is the centripetal acceleration, right, toward the center of the circle. So let's replace a with v squared over r, and look what happens. We end up getting mv squared over r, which is the centripetal force. The centripetal force is the net force. It's still saying m times a like it was in all those other problems that we've done, but this time we're tailoring that equation to this specific case where the object is moving in a circle. Remember what I said last week? Centripetal force is not a fundamental force. It's not a force that acts on its own ever. It's always a force that's caused by something else. The Earth going around the sun, the centripetal force, there is a centripetal force, but really what it is a force of gravity. The keys going around my head, there is a centripetal force, but really what it is a tension in the rope. A car going around a turn, there is a centripetal force, but really all that centripetal force is friction that acts toward the center of the circle. Here, when a car goes around a vertical circle, there is a centripetal force, but really all it is gravity and the normal force combined. Right? The centripetal force is mv squared over r, but that's just really another name for gravity and the normal force combined. Now we got to worry about plugging numbers in. And of course, when we do that, we got to worry about signs, positive or negative. Let's go through the easy one first. Gravity. Gravity, positive or negative at the top of the circle? Jen, is gravity positive or negative when you're at the top of the circle? Negative, because it's acting down, right? In fact, gravity at the bottom of the circle is also going to be negative because gravity is always acting down. The normal force, Reese, when you're at the top of the circle, positive or negative? How come? Good, because the normal force is acting down, it's going to be a negative value. Notice I've got it drawn as or listed as a positive number right now. I don't ever worry about negatives until I go to sub numbers in. So that would be the next step. What about the normal force when you're at the bottom of the circle? It can be positive or negative. William? How come? Good. It's positive because it's acting up. Now this is the tricky one, the centripetal force. The centripetal force, when you're at the top of the circle, acts which way? David? Let me give you a hint. The centripetal force, no matter where you are in a circle, no matter whether it's a vertical circle or not, the centripetal force always acts toward the center of the circle. Right? Centripetal force, center-seeking force, always points towards the center. David, when you're at the top of the circle, where is the center of the circle relative to you? Good. Below you or down. So we're going to make the centripetal force there, as soon as we start subbing numbers in for it, we're going to make it a negative number when you're at the top of the circle. What about when you're at the bottom of the circle? Maybe even a little bit harder here. We got, this one's not quite as bad because both forces are acting downwards. The net force of the centripetal force has to be downwards. But what about at the bottom, where one force is down, one force is up? Which way is the centripetal force now? Miles, which way is the centripetal force here? Sorry? How come? Good. Good. It's got to be toward the center, and the center of the circle is upwards relative to you when you're at the bottom, so it's going to be a positive value. Now remember, all those signs, those are great, but we're not worrying about them until we actually sub numbers in. Anytime we see a vertical circular motion question, it's going to start out like this. Whether or not the object is at the top of the circle or the bottom of the circle, everybody has a place to start. If you forget the signs or you get mixed up with positives and negatives, all right, you're going to get the question wrong, but you're at least going to have a start to the question because they always start the same way. All right, that's it, basically. And we've done, at this point, we've done problems like this, right? It's just a matter of setting it up so that we know what it looks like, and then it's just a matter of F net is the sum of the forces and sub your numbers in and solve what you're looking for. Let's take a look at example 5.7 on 264. It says a bucket of water with a mass of 1.5 kilograms is spun in a vertical circle on a rope. A bucket of water? Can you swing a bucket of water upside down? Not have it fall out? Really? If a bucket is upside down, if this is your bucket, and this is the water in the bucket, is it possible if the water's not frozen? Apparently, it just says in the question. Maybe we'll try that in a couple minutes and see if it's possible. The radius of the circle is 0.75 and the speed of the bucket is 3. What's the tension in the rope at position C, as shown in figure 5.31? All right, well, let's draw a free body diagram. They've pretty much already done that, actually, right? They've got FG. What do they have labeled upwards there? FT? What do we call it when we do our diagrams as I was starting this lesson? We call that FN, right? You want to call it FT? Go ahead. I'm going to continue to call it FN. Even though it's a tension in the string, I'm still going to call it the normal force. Next step, always the same. F net is equal to the sum of the forces. Again, I'm calling it FG plus FN. You want to call it FG plus FT, go ahead. Net force is mv squared over r equals force of gravity plus the normal force. Start subbing some numbers in here. M is 1.5. V is 3.00 squared. R is 0.75. FG, that's 1.5 times 9.81. And we're looking for Fn, or we're looking for the tension in the rope right there. Let's pull out a red pen, though, and start worrying about negatives and positives. When you're at the bottom of the circle, Miles, the bottom of the circle is centripetal force, the mv squared over r, positive or negative? The centripetal force, mv squared over r. Yeah, it's positive because it's upwards, right? You're at the bottom, the center is upwards from you, it's going to be a positive value. Okay? If you forget to even check, well, you're going to get lucky with that one because it's positive. What about gravity? Am I positive or negative? It's going to be negative because it's acting downwards. It's always going to be negative, right? In this context. Solve for Fn. All right, let's see what we can do here. We do the math on the left-hand side, it works out to be 18 newtons. On the right-hand side, 1.5 times 9.81 is negative 14.73, 71, 14.71, 72, plus Fn. Let's take this over to the other side now by adding, and I get Fn is equal to 32.72 newtons. Or I can say Fn, the normal force, the tension in the rope, is equal to, should round it to two digits there, 33 newtons. This should not have an absolute value sign around it this time, because in this equation, we are finding the direction. A positive means up, a negative means down. So it's not an absolute value of magnitude at all. It is the magnitude and direction of the force. Look, the normal force is 33 newtons. Gravity was 14. That makes sense, right? The normal force has to be bigger than gravity if you're at the bottom of the circle. Otherwise, it won't stay in the circle. I'm going to have you guys look at two questions on page 264. Anybody tell me why? Let me just copy over that diagram in example 5.7, and I'll ask you to tell me why I'm not asking you to do question number 2. Here's the picture. Why am I not asking you to do question number 2 here? Why am I not asking you to do question number 2, Fraser? Go ahead, Rosie. Yeah, it's at position B. We want to deal with A and C, right? The top of the bottom, those are the extremes. We could deal with this at position B. Instead of having a free body diagram like this, or gravity and the normal force like this, though, at position B, the normal force would be like this. Gravity would be like this. Do you guys know how to deal with that? Sure you do. It's just a two-dimensional force problem, right? We can't say F net is equal to the sum of the forces. We'd have to use a two-dimensional analysis. We could do that, but there's not really any point to doing that because the values that you find end up in between the values that you get at A and C. These are the extremes, so these are really the only important parts, A and C. So do question 1, please, and do question 3, please. Now let's have a look at question number 3 now that you've had a chance to work on it. It says a 0.98 kilogram rock is attached to a 0.4 meter long rope. Spun in a vertical circle. The tension on the rope when the rock is at the top of the swing is 79 newtons down. What's the speed of the rock? So here we go. Here's the circle that the rock is in. Okay, here's the rock. Let's not worry about drawing in the string per se. This is a free body diagram showing the forces acting on the rock. We know that this 0.98 kilogram rock has a normal force acting down, or you may have called it the force of tension in the rope, but regardless of what you call it, it's something is pulling it downwards. We also have a force of gravity acting down. How they compare in magnitude and in length, we don't really know that right now, so it doesn't really matter how long you draw those two forces, but they both should be pointing downwards. We want to find the speed of it. And we know what to do here, right? Everybody knows what to do here. Everybody in this room at least knows how to start this question. Okay, when we see a free body diagram with two forces, then we say F net is equal to the sum of the forces. Everybody has got to get this far. Everybody has got to get this far because every one of these questions is exactly the same to this point. Now let's start plugging in some numbers here, okay? The mass is 0.98. V, we don't know. That's what we're trying to find. R is 0.40. The normal force, that's where, oh wait, we do have the normal force. It's 79 newtons. That's the tension in the rope. And the force of gravity is 0.98 times 9.81. Let's worry about negatives and positives here. Okay, gravity, first of all, because that's the easy one. Gravity going to be negative or positive ever? Negative, because it's acting downwards, right? The normal force, when you're at the top of the circle, is a normal force acting positive or negative, Tori? Normal force. It's negative because it's acting downwards. Good. And what about the centripetal force? Look, I plugged in numbers for that as well. I haven't finished. I'm looking for one of the variables in there, but I've started plugging numbers in for the centripetal force. Is it going to be positive or is it going to be negative? Jana? Negative because it's acting downwards toward the center of the circle. Even though I haven't finished plugging in the value for V, I still want to plug in a negative value, a negative sign for that. All right, let's do this now on our calculator. Let's say 0.98 divided by 0.4 gives me 2.45. So I've got negative 2.45 V squared. Now on the right-hand side, I'm going to have negative 0.98 times, is that 0.98? Yep. Negative 0.98 times 9.81. Okay, that's going to be the force of gravity. Subtract 79 newtons, that's the normal force. So on the right-hand side, I have negative 88.6138. I'm going to divide that by negative 2.45. Get it right here one of these days. There we are. Gives me 36, and then I'm going to square root that. And I end up getting 6.01, or to 2 digits, 6.0 meters per second. And what do you think would happen if I was going faster? How would going faster affect the force of gravity? Anyone? It wouldn't, right? It wouldn't. If I went faster, the force of gravity is still the same. Stefan, if I went faster, how would it affect the normal force, this value of 79 newtons? It's a tough one, eh? I'm not asking you to calculate something. I'm asking you to use just some logic on that. If I went faster, the string would have to pull less or more. Okay, here's the keys going around my head. Okay, going slow. If I swing it faster, does the string have to pull less or more as it goes faster? More. So the tension or the normal force would be bigger, right? All right. Now, let's go a step further with this. We did a little demonstration of the water going around in the vertical circle. We kind of rocked it back and forth before we started it going, right? We rocked it back and forth because we knew that it had to be going fast enough to go around the circle. If it's going too slow, then we're going to get wet as we're swinging that water in a vertical circle. If a roller coaster is going too slow in a vertical circle, it will fall off. It won't really, because they have safety mechanisms built in to prevent that. But in the absence of those safety mechanisms, going too slow, the roller coaster falls off. You go to a skateboard park and you see one of those things, what do they call it? It's like a concrete tunnel that goes all the way around, and try to skateboard all the way around it upside down. If you're going too slow, what happens? You fall, right? If you're going fast enough, you go all the way around it upside down. If an object is moving too slow, it's not going to make it around the circle. Watch my keys as I swing them around, though. Right now, I'm going clearly fast enough to make it around a vertical circle, right? Watch as I slow down. Okay, watch as I slow down. What happens? If I go too slow, the keys didn't make it around the vertical circle there, right? I want you to look at what happens to the string and what happens to the lanyard here that I'm swinging around just before it falls. So I'm going fast enough to go around a vertical circle. I'm going fast enough to go around the circle, but barely. What do you notice about the string when I'm barely fast enough to go around the circle? How hard does the string have to pull, David? Right. When you're going at barely the minimum speed, and there is a minimum speed, right? Because below a certain speed, you don't go around the circle, and above the speed, you do. When I'm barely going the minimum speed, gravity does all the work. Gravity provides the entire centripetal force. The string doesn't have to pull down at all. Now, above that minimum speed, gravity still pulls the same force. So above that minimum speed, then the tension in the rope, or the normal force, has to help gravity. But at the minimum speed, gravity does everything. So we're going to say here that object not making it around the top of the circle, it's going to fall out at the top of the circle, not at the bottom. And at this point, the point where it barely makes it around or barely falls out, the tension in the rope, or if you're going on a roller coaster, the force on the track, at that point would be 0. So what we're going to do in just a moment here, after you finish copying this, is calculate the minimum speed necessary to move around a vertical circle without falling out. And when we do that, to find that minimum speed, we're going to set it up the same way as we've set up the other problems that we've done, except that we're going to make the value of Fn automatically 0. At minimum speed, Fn equals 0. Going slower than that, hey, it's a projectile motion problem. I'm going slower than that because look what happens to the keys as I'm going slower than that. They go in a parabola, right? They follow it and they go in a parabola. If I'm going faster than that, yeah, well then it's a circular motion problem, but Fn isn't equal to 0. It's not a minimum speed problem. At minimum speed, the normal force is equal to 0. Same problem as we had before, except Fn is 0. Yep. Yep. So look at this problem, please, on page 262. This is a 700 kilogram roller coaster full of people, goes around a vertical loop that has a diameter of 50 meters. I'm going to actually draw attention to that, right? Because I don't want diameter, I want radius. You got to remember to divide that by 2. What's the minimum speed roller coaster has to have at the top of the loop to stay on the track? Let's draw it. Here's the roller coaster. At the top of the circle, we would usually have a normal force and a force of gravity. And at the top of the circle, we'd say F net is equal to Fn plus Fg. But in this case, since we're looking for the minimum speed, Fn is 0. Below that speed, it's not a circular motion problem. Above that speed, it is a circular motion problem, but we're not going to find the minimum speed. mv squared over r equals, now it's just m times g, because Fn disappeared. Now, mass will actually cancel. So the good news is, next month, for you guys go on your field trip, you happen to get on that roller coaster and there happens to be a 300-pound man sitting beside you. You don't need to worry, oh my goodness, he's too heavy. We're going to fall out of the loop, the upside down loop. It doesn't make any difference. Why? Force of gravity acting on him is bigger than the force of gravity acting on a little kid. But the inertia taking him in a straight line is also bigger. So in the end, he's heavier, doesn't make any difference in terms of the minimum speed going around that circle. They kind of balance each other. Okay, let's solve for v here. V squared over 25 meters is the radius, equals 9.81. And technically, both of these are negative because we're at the top of the circle. Say 25 times 9.81. Negatives end up canceling here, though, right? Because it's in both terms. 25 times 9.81. Now let's square root that. We end up getting 15.7. meters per second. You go above that, all is good. You go below that, watch out, because you're going to fall out of the loop. You're not going to fall straight down, right? You're moving, you're going to, once you leave the track, it's going to be a parabola. But you're still going to fall out of the track, which is not what you want to happen when you're on a roller coaster. All right, let's have a look at page 262, questions 1 and 2, please.